Hello. Hello. So let's look at the first question. Right. So the first question says that we are given this matrix P in R4 cross 4, and uh, and which of the following corresponds to a QR factorization. So to do a QR factorization of P, the matrix R is given, and and we need to state uh, which of the following matrices is a value of R. So uh, what do we know about QR factorization? Well, the QR factorization is going to be unique uh, if we make the assumption that the diagonal entries of the R matrix is is positive, right? So a way to check this would be just as follows. You're given these matrices, you have to check PR inverse basically, and if PR inverse is orthonormal, uh, then okay, it should be orthonormal and R should be upper uh, upper diagonal. Yeah, so this is more like a computational problem. For each of these matrices, you should check uh, P uh, times R inverse. Um, so some of the options are obviously not feasible, like this one, for instance. This is not even an upper diagonal matrix. For this matrix, the entries can be easily computed because uh, yeah, for these entries, these can be very easily computed because uh, uh, this is obviously not feasible. Uh, this is a diagonal matrix, so its inverse is just going to be the inverse of its diagonal elements. And you're left with B and C, B and D to compute. Suppose you don't want to explicitly compute the inverse, then there could be a possible shortcut way, which is as follows. So if Q is equal to P times R inverse, then you know uh, that the determinant of Q should be equal to plus or minus 1. Okay, this follows from the fact that that Q transpose of Q is equal to I, and so determinant of Q transpose Q, which is determinant of Q, sorry, uh, which is determinant of uh, Q squared, must be equal to 1, right? Uh, and so you can, so as like a sanity check, you can check the determinant. So determinant of PR inverse should be equal to plus or minus 1. uh, which is that determinant of P by determinant of R should be equal to plus or minus 1. So, yeah, so one thing that you can check is that the absolute values of the determinants of P and R should be identical. That could be one way to eliminate an option. Okay, but otherwise you have to explicitly perform this computation. All right, let's move on to the next problem. I'm not explicitly doing this computation. This is routine. Okay, on to the next problem, the second problem. So in this problem, we want to solve Ax equals b uh, using a QR decomposition. Okay, what is the standard way of computing R? Oh, okay. So the standard way of computing R is as follows. I assume we're talking about this problem only. Right. So, I mean, what is the uh, what is the QR decomposition? You're writing a matrix P as Q times R. Right. Now, now if you write this Q in this way, let's say Q1, Q2 up to Qn. So these are actually column vectors, right? And R is some upper triangular matrix. Okay, right. So what happens is that if you write this P as P1 up to let's say Pn, then you basically have to solve for this thing. So P is known, you have to solve for Q and R. And the way you solve for Q and R is as follows. So you write this P1 is the first you write P1 is equal to Q1 times R11. So think of this R matrix. So R is an upper diagonal matrix. So its entries are going to be R11. Let me just write it here. Uh, R11, and these guys will be all zero. Then this is R12, R22. Okay, and these guys are going to be zero. So you have to basically solve for each of these variables, and you also have to solve for the matrix Q. Okay, right. So first P1 is equal to Q1 times R11, right? So now what happens is that you know that these are so Q is basically an orthogonal matrix. So each of its columns are going to be orthonormal. So Q1 mod is equal to 1, right? So if you take the norm of both sides, then this is equal to 1. and you want this. So essentially, what you want is R11 mod is equal to norm of P1. Now R11 is positive because you want this restriction that all the diagonal elements should be positive. So you have basically found R11. So R11 is equal to norm of P1, uh, norm of this P1. Okay. So for the next column, what you do is this. You write this P2 as equal to uh, R12 times Q1 plus R22 times Q2, right? Uh, right. So you know Q1. Well, what is Q1? Q1 is equal to P1 by R11. Okay. Remember, Q1 is a vector. This is a column vector. P1 is a column vector, and R1 are the scalars that I'm computing. So, so essentially, P2 minus R12 Q1, sorry, Q1 is equal to R22 times Q2. Okay. Now again, you apply the same trick. So this is a known vector now because you solved for Q1 and R12 is right. Uh, this is actually going to be equal to 1. So what you can do is, yeah, 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 yeah. This entry is going to be 1. Sorry. Yeah. Yeah, essentially, what the just to instead of doing this, one thing which you can do is you can do the Gram-Schmidt orthogonalization process. Uh, so in the Gram-Schmidt orthogonalization process, I mean, what do? You start off with a set of vectors. Let me just write it over here. Right. So you start off with a uh, set of vectors, and these are column vectors, each of these, and you want to find out a corresponding set of orthonormal vectors uh, which have the same span as these vectors, right? So you first set Q1 is equal to P1 by norm of P1. Okay, so that is your Q1, right? So next time, what you do is uh, you write another matrix Q2. Sorry, you set Q2 as equal to P2 minus uh, just give me 1 second. Just give me 1 second. I think someone has posted something. Just give me 1 second. I'll be back in 1 second. Yeah, sorry. I'm back. Yeah, so you write this Q2 as equal to P2 minus um, the projection of P2 on Q1, which is this. So you write this P2 on Q1 times Q1. So notice that this vector Q2 is going to be orthogonal to Q1, right? You can check that Q2 minus Q1 is going to be equal to 0. But this is going to be, but this did not be orthonormal, so you orthonormalize it, right? Uh, so you define this vector Q2 bar as equal to Q2 by norm of Q2, right? So your Q2 uh, hat is equal to P2 minus P2 Q1 Q1 times Q2 hat. Right. But what is this Q1? So this Q1 is equal to is P2 times Q1. This Q1 is equal to P1 by some P1 norm by this Q2. So if you have to now write this as a if you want to write this Q2 as a linear combination of matrix of P1 and P2, well, what is the appropriate linear combination? Well, the linear combination is this. Um, if this is P1 and if this is P2, then the linear combination that you should put over here is uh, is 1 by uh, Q2 and basically this term over here. So you write this term as R12, then R12 is equal to minus P2 comma Q1 by norm of Q1 times norm of Q2. And this is your R12 term. Right. And likewise, you solve uh, for the rest of these entries over here. It's just the Gram-Schmidt orthogonalization, and you keep on producing the entries in this way, right? Okay. If this is clear, then I'll go on to the second problem. Right. I mean, this is essentially the same thing as saying basically this. So, uh, if you write the second equation, I mean, it's just a Gram-Schmidt orthogonal. You can do explicitly the orthogonalization, or you can just keep on solving the equation. So, just write, let's say, P2 is equal to R12 times Q1 plus R22 times Q2. Okay. Now, you want that Q1 and Q2 are orthogonal to each other. So this is 0, right? So you take an inner product with Q1. So if you take an inner product with Q1, then this term drops to 0, and Q1 inner product with itself is 1 because Q is a unit norm vector. So you get this. So you get P2 uh, times Q1 inner product is equal to R12, right? So now R22 times Q2 is equal to P2 minus R12 times Q1. R12 is something that we have found out. Again, you take the norm of this side. Okay. Uh, this is equal to 1 because you want it to be a unit norm vector. And R22, you can take it to be equal to just the norm of this thing. Um so what happens is that R22 is equal to P2 minus R12 times Q1. Okay. And this matrix Q2 is equal to, of course, uh, P2 minus R12 times Q1 by uh, R22. And likewise, you can solve it. It should be clear now. Yeah, similarly, you can write this P3 uh, as equal to R13 uh, Q1 plus R23 Q2 plus R33 Q3. Right. And this time you first take an inner product with Q1, next an inner product with Q2. Uh, every time you take an inner product, you will get basically this factor. So this thing comes out. So basically R13 is equal to P3 inner product with Q1. R23 is uh, P P3 inner product with Q2. Okay. Uh, and R33 uh, is going to be the norm of P3 minus R13 Q1 minus R23 Q2. Okay. And that's how you can keep on uh, computing R. Okay. And you know that this is always going to be unique. So however you compute it, you will always get this. As long as you assume that these diagonal entries are always positive. If you make them negative, if you take negative of this thing, then the matrix also the Q3 3 would also have to be negated appropriately. Okay. Yeah, I hope this is clear now. Let's look at the second problem. Uh, okay. So in this problem, we have a matrix A, and we want to solve for uh, Ax equals to B using a QR decomposition. But the QR decomposition requires us to build this this Q matrix um, using rotators. Okay. So I hope you know what a rotator is. Okay. Um, so in short, if you have a I hope you know what a rotator is. This was discussed in the lecture. I noticed it's there in the lecture material. So I'm not going to define what a rotator is. Uh, right. So so what we need to do is this Q matrix that we're going to construct. This has to be through rotators. Through rotator. Essentially, what it means is that I should be able to write this Q as a product of some QJs, where each QJ is a rotator. And just so that it's clear, so essentially, what a rotation is doing is, um, uh, if I can draw a picture. So let's say you are in Xn. Sorry, let's say you are in Rn. Uh, I'm going to quickly draw a picture like this. Uh, so let's say this is the ith axis. This is the jth axis, and think of this line as Rn minus 2. Okay. So this is not a this is like just a symbolic picture. This line is actually the entire n minus 2 dimensional subspace. And what each rotation matrix is doing is that if you have a matrix, if you have a vector which is x1 to xn uh, represented in the standard basis, okay, so it is rotating just the ith and the jth. So you project. So let me just write it down over here. Project uh, x onto the uh, ij axis. So well, what's that's going to be? So x1 to xn uh, would go to xi comma xj. So there's some point over here, xi comma xj. Let's say. And you then rotate it, you pick some angle theta, and you rotate it by some angle theta, goes to some xi prime and xj prime. So the effect of applying this transformation is as follows. So this x1 up to xn now goes to, so x1 up to xi minus 1 remains invariant. Uh, xi changes to some xi star. Then the other guys remain invariant. Xj changes to some xj star. And again, the other guys remain invariant. Okay. So, yeah, so essentially what is happening is this. So you know that in 2D, any rotation, you can write it in this way. When R2 cross R2, sorry, in R2, in R2, any rotation by theta uh, looks like this. Yeah, for Rn, you are not changing. You are keeping. You're only changing the ith and jth coordinates. The rest of the coordinates remain invariant. So that uh, so that a unitary rotation in any one plane looks like this. So it has all ones, uh, but in the ith uh, in the ith uh, column, it has cos theta. This is the ith row, ith column. Similarly, there is this jth row, jth column. Okay. At j, this is sine theta. This is minus sine theta here, cos theta here, and the rest are all ones again. So, so any matrix of this kind is what we are calling a rotator. Yeah. Right. So it has this effect of rotating by this angle theta. Okay. And hello, can you hear me? Or is there no audio there? Just give me 1 second. Is there audio? Can anyone just unmute and say if you can hear me?
Yes, sir. We can.
Okay, I mean, someone just posted in chat there's no audio. I guess for that. I guess can you just check now that person?
Hello, sir.
Yes.
Sir, I have one question about flops.
Yeah.
May I ask?
Sure. Yeah. Yeah.
Uh, yes.
Yes. Please ask.
Yes, sir. Sir, actually, जब ये complexity find करते हैं, uh,
Hmm.
then suppose it is n square minus n by 2. That is the total number of operations, and
Right.
we yes, and we write it approximate to n square.
Right.
So means we always take approximate value.
No. So the notation is a this is called the big O notation. Uh, so in big O notation, what happens is that uh, you look at, so if your complexity is some polynomial in n, uh,
Mhm.
then you look at the highest degree of that polynomial. Okay, and that is your complexity. So
And
let me just write
sometimes,
it.
sir,
Uh, yeah, go
uh,
on.
s- sometimes, sir, you are writing means approximate to 4 n square by 6. So
Ha, ha,
here
ha.
we are taking its coefficient factor, means 4 by 6.
Yeah,
So
yeah. So what you do is you
in this
ignore this
case, we
4 and
cannot
6.
take only n square.
Yeah, in this case, so let's say you calculate the number of flops, and the number of flops comes out to be something like, let's say, an squared plus bn plus some c, something. Okay. So in that case, you simply uh, you think that there are no coefficients here. Okay. You just look at the highest degree term there, and the highest degree term decides your complexity. Okay. So the
Uh,
complexity of this term would be O(n) squared. And the reason, so I mean, what complexity means is that uh, uh, so you say that something has a, I mean, this is a concept in computer science. So you say that a particular term has a particular amount of complexity. If you divide it by it and take like appropriate limits and tending to infinity, then this would tend to a constant. So essentially, what I mean over here is this. So if you write an squared by b plus bn plus c, and if you divide it by n squared, right? And if you take limit n tending to infinity,
yes,
then what happens is that all these, this both of these will drop off, right?
we get
And you will
only
get, yeah, and you will
A.
get it to be equal to a, right? So that is the reason why we say the complexity is O(n) squared. We say that something is O, right? So let me just write it over here in case you're not familiar with it. So we say uh, n, right? One second. We say f of n and g of n have the same complexity.
Bye, Chotu. Chotu. Bye bye. Bye bye. Good night.
Okay, so we write Fn is O of Gn if limit n tending to infinity, Fn by Gn
Bye.
is a constant. Okay. So therefore, an square plus bn plus c and n square have the same complexity. So you can write an square plus bn plus c as big O of n. Um, okay, yeah, hope this is clear.
Sir, excuse me, sir.
Yes,
Sir, I also have doubt on question number 1,
yeah,
assignment question number 1.
yes,
Sir, actually, in the theory notes, we take matrix A as a square matrix, either 2 cross 2 or 3 cross 3 or n cross n. But
ha ha ha,
here we take P as a 4 cross 3. It is not a square
yes,
matrix. So in
yeah.
this
It
case,
doesn't have to be a square matrix. uh, doesn't have to be a square matrix. So I guess you joined now.
yes,
I, I I was describing this problem before. I can quickly run you through in case you don't get in case you don't understand what I'm saying right now. This entire thing would be posted on YouTube, so you can then go back and look back at it. But I'll quickly run you through what happened or how to exactly get this computation because you don't have a lot of time left. So right, so right. Like आपको basically क्या करना है? I'm changing my language to Hindi. I
yes,
think
sir.
okay, I'll just stick to English only for everyone's sake. Right. Okay.
Sir, I am
So
also compared in Hindi if you use Hindi.
but I think we have to stick to English. I think I don't know if everyone is comfortable with that.
Okay.
Uh,
Okay.
okay, so we are computing this P equals to Q or R, right? And R is a diagonal matrix. Sorry, R is an upper triangular matrix. So R
Yes.
looks like this, something like this. Okay, and Q is a Q is an
Orthogonal.
orthogonal matrix. Right. Now, but the thing is, Q cannot be, so if P is not an n cross n matrix, like in this case, P here is a, yeah, it's a 4 cross 3 matrix, right? So then Q also is going to be a 4 cross 3 matrix, but R is going to be a 3 cross 3 matrix. So if you write this Q as Q1, Q2, and Q3, each of this Q1, Q2, Q3 are actually vectors uh, in R4. So this is a column vector, this is a column vector, right? Now you want Q1, they are all orthogonal to each other. So Q1 inner product with Q2 is equal to 0. And likewise, they're all mutually orthogonal to each other. So basically, Qi uh, inner product with Qj is equal to 0 if I is not equal to j, and equal to 1 if I is equal to j, right? So this is one constraint, and using this constraint you have to basically solve for this thing. So I wrote over here, uh, yeah, so you will write this P1 first as R11 times Q1, then P2 as equal to R21 times Q1 plus, um, sorry, not R21, R12. R12 times Q1 plus R22 times Q2. Okay. Now you have to solve for these things. So you know that the norm of this is 1. You have to basically solve for R11, Q1, R12, Q1. You have to solve for each of these variables. And when you solve for each of these variables, that will give you your Q and R respectively. So now you may think that, okay, there are too many variables to solve and too few equations, but that's not actually the case. You have additional constraints with you, and the constraints are that each of these QIs have unit norm, and the QIs and QJs are also orthogonal to each other. So you have to use this fact. So let's say you want to solve this first equation. So this is unit norm. So if you take the norm of this side, this is equal to 1. So you get R11 norm, mod of R1 is equal to P1 norm. Okay. So you have got the value of R11. So once you get the value of R11, you know the value of Q1. You simply divide it. Right. Next, uh, next you have to solve, let's say, this equation. P2, R12, Q1, Q2. Now Q1 and Q2 are orthogonal to each other. So if you take an inner product of Q1 with Q2, let me write it here. So P2 inner product with Q1, then this term drops to 0 because Q2 and Q1 are orthogonal to each other. So it becomes R12 and Q1 uh, inner product with itself is the norm of Q1, which is 1. So P2 comma Q1 is equal to R12. So you have got the value of R12. Q1 is already known to you. So now you have R22 times Q2 is equal to P2 minus R12 times Q1. Again, you apply the same trick as before. So Q2 has to be norm 1. So that means that uh, R22 mod is equal to norm of P2 minus R12 times Q1. Okay. So that's how you get the value of R22 and the value of Q2. And likewise, you have to keep on solving for all those equations. So if there are uh, so if there are three columns over here, you will also your Q matrix would also have three columns. Okay, so it doesn't have to be an n cross n matrix. Um, okay, all right. Let's go back to the second problem. So in the second problem, the matrix that we're looking at, A, uh, uh, the Q over here is constructed using rotators. So basically, I'm going to write A as a product of these rotators. And yeah, so one thing that we know is if you have any vector, not a matrix, just a vector x in Rn. So let's you write this x as x1 up to xn transpose. Then you can construct a sequence of rotators, um, which makes this x. Okay, let me just write it. I'm not going to prove it. It's there in the notes. There exists a sequence of rotators uh, q1 up to qn, such that if you apply them qn up to q1, if you apply it on x, then x looks something like this. Okay. Now your A matrix over here has to be transformed into an upper triangular matrix. So the way to do it is that you first apply a sequence of rotators that changes. Let me just write it. Apply rotators that changes first column into this form. So you start off with A and apply a sequence of rotators. Let's call them Qn comma 1 up to Q1 comma 1, which if we apply on A, then your matrix now looks like this. Um, right. The first column has now become only the first entry of this first column is non-zero. Rest everyone is zero. And the rest of the matrix may have changed appropriately. Doesn't matter. Okay. So now you apply this process again, but this time you do it for with respect to the second row. So again, you apply a series of transformations. I'm going to write it as qn comma 2 up to, let's say, uh, q2 comma 2. You apply on this matrix. Let's call this matrix A1. You apply it on A1. And when you apply this on A1, uh, this call only this and this entries are non-zero. So these guys now become equal to zero. So the this could be non-zero as well. This entry could be non-zero as well, and the rest of the matrix is uh, as it is. And in this way, you iteratively keep on multiplying these rotators until you get a upper triangular matrix. So yeah, so so for making the first column into this form, you need to apply n rotators. For this, for the second column, n minus 1 rotators. And likewise, the total number of rotators you need to apply is n plus n minus 1 up to 1, which is O of n squared, right? But you have to compute the total number of flops that is
Excuse me,
moving.
sir.
Yeah.
Sir, I think it will start from n minus 1, n minus 1, n minus 2 up to 1, or it will start n.
Yeah. Okay. Okay. It doesn't matter. I mean, uh, let's say it starts from n minus 1 up to n, then you get something like
In first
n into
column,
n.
there are n minus
Yeah.
1 entry.
True, true. Yeah, you're right. Sometimes what happens is when we're doing these complexity calculations, uh, whether you get n into n minus 1 by 2 or n into n plus 1 by 2, it doesn't
Yes,
matter
it
because this is
approximate to
n
n
squared
square.
and this is also n squared. Yeah. So
Yeah.
sometimes we overestimate, but that won't change the complexity estimate. Yeah, maybe I was overestimating. That's true. Yeah, you're correct. You're correct. Right. And yeah, so this is O n squared. But every time you multiply the matrix, this this again takes O n flops to multiply. ON is not an exact number. There is an exact computation, which I'm not going to write. There's no point. Uh, but the total complexity is ON to do a multiplication, and total number of multiplications is O of n squared, which makes the complexity as O of n cubed. Yeah, you can always multiply complexities. Uh, if there's something under the O sign, you can always multiply the two of them, and it will always be uh, so basically, what I'm saying is the complexity of Fn uh, times the complexity of Gn uh, is equal to the complexity of Fn times Gn. This is true. Okay. Uh, so yeah, we know the answers now.
Sir, excuse me, sir.
Yeah.
Sir,
Yes.
this is the complexity for decomposing matrix A into QR. But
Yes.
in the question, I think he is asking the complexity to solve the equation AX is equal to B.
Ha 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 ha.
So,
Ha.
what will be
Right.
the complexity for this equation to solve?
Right. 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 Okay. Uh, okay. So let's say you have found out A equals to some QR. Okay. So now you will write QR times X is equal to B. So you will write Rx is equal to Q transpose B. So what is the complexity of computing Q transpose B? Complexity of computing Q transpose B of is O of n squared. Multiplying a matrix with a vector takes O n squared. Right. Uh, and then you have Rx equals this Q star B. Write this. You can write this Q star B. Sorry, this Q transpose B as B star. Okay. But R
Sir,
is a
sir here
yeah.
X is a vector in Rn.
Yeah, X is a vector. X is a vector. That's right. X is a vector
Okay.
in R.
Mhm.
Yeah, you have to solve for this thing. Yeah. So now you are applying back substitution on Rx to solve B squared. Back substitution, well, I mean, um, back substitution will again take On squared steps. So the costly part is actually computing the QR decomposition. The Once you have computed the QR decomposition, solving the equation happens in On squared steps. Okay, so the overall complexity remains ONQ. Okay, yeah, I was not solving this. I was kind of leaving it as an exercise, but okay, since you pointed it out. All right. Look at the next problem.
Sir, so here we will add the complexity first,
Yes, yes,
decomposition
yes.
of complexity
Yes,
and on solving for this.
yes. There are two steps. Yeah, there are two steps. The complexity gets added up. Okay.
Overall complexity will be the higher degree,
Yes.
n cube.
So there's one policy uh, in our sessions, which is that uh, uh, it was agreed upon in my first session that I would not fill out the exact answers to the assignment because I understand that the week is still going on and the
Yes.
submission due date is still not over. So
No,
since
I'm not asking answer. I'm just asking that here we will add
yeah,
these
yeah, yeah,
two
that's fine, that's fine,
complexity.
that's fine. That's fine. So sometimes what I'll do is I may not. So you will see some questions later on where you are asked to compute some things. So in that case, so let's say which involves like doing some matrix multiplication or something like that. So I will not actually do that exact computation. Because those
This is
I
not
will just
exactly computation. I'm just asking that there is a two steps. So in two
true, true.
steps
Yeah, yeah,
we
yeah.
add
That
the
is, yeah, yeah,
complexity. Na?
that, yeah, yeah, exactly, exactly, exactly. No, no,
Okay.
I'm just making, I'm not talking about this particular question. I'm just saying that in general, I will not solve a problem exactly. That's what I'm
Yes.
trying to
Yes. Okay. Means if a problem is divided into two or three steps, so for complexity, we
say.
first
Yeah,
find in each step complexity
hmm,
and then we add.
yeah, yes, right.
Okay.
That is the rule for finding complexity. Yeah,
Okay.
and BIGO, and when you use this BIGO notation, you can just add and multiply things. Uh, so you can add and multiply under the BIGO notation.
Okay. Hmm.
That's the thing.
Thank you.
Okay. So now the third problem is we have a unit lower triangular matrix in which all the diagonal elements are equal to one. Uh, so some matrix L such that uh, L is some lower triangular, such that this LII is equal to one.
Excuse me, sir.
Uh, yes.
Sir, if possible, then can you first come to question 6? Actually, I have
No,
only
I'm going to
one
solve these
question
questions.
in
I'm going to
sequence.
solve these questions in sequence. Yes. Uh, I'll take maybe like 15 minutes to come to question
Ji?
six. I'll take like 15 minutes to come to question six, not more than that. You just have to wait for like 10, 15 minutes. I'll be in question six in 10, 15 minutes.
Okay,
Okay.
okay.
Okay. Uh, right. So the first is this is like a true false question. This third question. Every unit lower triangular matrix has this many zeros. So in every lower triangular matrix, uh, Li uh, Lij is equal to 0 for yeah, for j less than I. Uh, yeah, no, this is an obvious question. Uh, every unit lower triangular matrix is invertible. Well, what can we say? I mean, if LIIs are equal to 1, then L is full rank. Okay. Well, it's going to be full rank because uh, you have ones in the diagonals. And if you, it's full rank because if you pick any columns, so let's say you pick columns Li1, Lik, and if you take any linear combination of those columns, so let's say you do some A1 Li1 plus AK Lik, then this linear combination is never equal to zero for or alternatively this is equal to zero if and only if a1 up to ak is equal to zero. Okay, so I hope the answer is clear now. Yeah, let's look at the next problem. Yeah, I'm not proving the statement. I hope the proof is clear. The proof is like this. Uh, if you take any linear combination of any one of the columns A1 to AIK, uh, then if if one of this is non-zero, so if one of these A1 to AKs is, or if at least one of these A1 to AKs is non-zero, then say let uh, let uh, uh, let S in uh, 1 up to K be the largest integer such that AS is non-zero. Okay, so if AS is non-zero, uh, then if you add, let's say, AS LIS plus AS plus 1 LIS plus 1 up to AK LIK. If you look at this column, if you call this column as some column, if you call this as some L prime, then L prime of S comma S uh, will be equal to S. It's never going to be equal to zero. And so the columns of L are always going to be independent. And so L is full rank. Okay. So these are the two statements that we can infer. And every upper triangular matrix is invertible. No, not necessarily. Okay. Um, look at the fourth problem. Uh, right. So every rotator matrix in theta would look like this: cos theta, um, sin theta, minus sin theta, cos theta. This is for theta being rotated anti-clockwise. For being rotated anti-clockwise, yes. When theta is rotated clockwise, you should replace theta by minus theta. Uh, so here the matrix is basically R of minus theta. Okay, and there are a number of identities over here, uh, which uh, uh, which checking those identities is routine. So I'm going now. I'm not going to uh, check those. So let me just write it. Uh, R minus theta is a rotation for clockwise. Check these identities. Okay. Uh, On to the fifth problem. Okay, so yeah, this is one example where we're given just a single vector v, uh, and we have to do a QR factorization of this. So, well, I mean, we're going to write v as equal to norm of v times some vector q, right? That vector q is going to be v times v by norm of v, and this is going to be the value of r. So, yeah, uh, an r, which is just uh, this is going to be a scalar in this case. Uh, is norm of v2. Okay, now on to the sixth problem. Okay, so yeah, you were asking me, you had some doubt in this question. Can you ask your doubt?
Actually, I can't understand the statement of the question. Means
Oh, okay.
in this, what they are asking about matrix E or U.
No, they're asking you to compute
I'm
a matrix
not-
E.
yes, matrix E, no? Yes.
Yes, matrix E is the question.
I'm not able to find the matrix E. What is the process?
Okay, so you want to find a matrix E uh, such that EP is equal to U.
Yes.
So what about QR decomposition? Well, you can write P as equal to some Q times U, where U is an upper triangular matrix. Q is an upper U is an upper triangular matrix. So in QR decomposition, U will be an upper triangular matrix, right? And Q is going to be orthogonal. So if you do Q transpose times P, that is equal to Q transpose Q U, and that's U. So if you do a QR decomposition of P and then Q transpose solves for E, right? So let me just write it. Uh, do a QR decomposition. Write P equals Q times U. Q transpose solves for E. But will it match with the four options that's given to you? That's the thing. it's not guaranteed that if you write EP equals U, then E and U have to be unique. There could be anything possible. There's no guarantee that it's going to have a unique multiplicator that leads to this U. Okay, and so uh, right, because the reason is that you can you can vary U, right? So if you write EP is equal to U, right? So what is the rank of P? Uh, let's do a quick rank checking. What is the rank of P? If you quickly compute the determinant of P, uh, determinant of P is equal to what? It's 10 times 10 minus 8 2 uh, then 0 plus 1 times uh, 8 minus 2 6. Yeah, so it's actually 4. So rank of P is equal to 3. Now there's going to be no unique solution, right? Because P is a uh, P is a full rank matrix. You can choose U to be any full rank. Uh, U could be any full rank uh, upper triangular matrix. In fact, you could take U to be equal to I3 as well. So the way you solve this problem is that you have to take each of these four matrices and then uh, explicitly perform a computation by hand and check which of them gives you an upper triangular matrix. So that's the way you solve a question like this. Because there's no
Sir,
unique solution.
I checked means from the options to multiply with the
Hmm.
matrix P, but in
Yeah.
every case we get upper triangular matrix.
So everything gives you an upper triangular matrix. Okay, then
Yes.
all of the options are correct. Yeah.
No, but there is option only for A, B, C, D. Uh,
Oh, and oh, then it could be a mistake in the problem. Yeah, it could be probably like a mistake in the question.
if
You sure there's
lower
only
triangular
hmm,
matrix, if lower triangular matrix is multiply with P, then we will
hmm.
get upper triangular
No, no,
because
no.
all are a lower triangular matrix.
Yeah, all are lower triangular matrix. Yeah, again, there's no guarantee that there's going to be a unique lower triangular matrix that gives you this. Right. No such guarantee. Yeah, you have to solve for each of them and check. And yeah, if you're saying that all of them give you the right answer, then
Oh, otherwise
because
I will
because
try it
because
again.
this U is
Multiply.
because this no because there cannot be unique solution, right? So let's say uh, uh, there is a lower triangular matrix L and you write L times P equals to some U, right? See, if U is upper triangular, you can uh, you can always you can always multiply U with a scalar, right? Let's say you multiply U with some scalar A and you multiply this thing also with some scalar A, then also this will be upper triangular matrix, this will be a lower triangular matrix. So there's no way you can find a unique solution. Okay, it can never happen. Okay. So yeah, in case it's a single option correct, then it's probably a wrong question, or the options are not right, or maybe it's a multi-option correct.
But they are given only for a single option A, B, C,
Yeah,
D.
in that case, I think in that case you may have to write to NPTEL and say that this question is incorrect. Okay,
Okay.
it's not uncommon to find incorrect questions. I've seen that in the past.
Maybe I checked just A, B, and in both case we get upper triangular. So I
Yeah,
will
then
check
then
rest
yeah
C and D
yeah.
also.
Okay, okay. Um,
Okay.
um,
Thank you.
yeah, sure. Okay. Um, yeah, so here there is some vector given u, and they're asking us to apply a rotator and see what we are getting over here. Um, so essentially, what is happening is as follows: find a vector v after rotating u 90 degrees counterclockwise around z axis. So uh, the picture is like this: this is z, this is x, and this is y. Um, there is some vector u uh, over here. Actually, there's a vector u over here. This is where u is, but u has a projection onto the xy axis. So this 1 1 becomes 1 1 0, and okay, find the vector v after rotating u counterclockwise direction onto z axis. I think, yeah, I think what they're saying is, yeah, I think what they're saying is that you rotate this vector by 90 degrees, uh, 90 degrees, and this component remains the same. So I think the rotator matrix is going to be this. The language over here is a bit confusing. I'm not sure what exactly they mean. I think it's going to be this though. So this matrix is, it has two blocks. This is a 2 cross 2 block, and this is one. Yeah, and this rotation is a pi by 2 rotation. So it's a rotation by pi by 2. Uh, cos pi by 2, uh, sin pi by 2, minus sin pi by 2, cos pi by 2. Yeah, I think this is the rotation matrix to consider here. No zeros. Yeah, I think this is the matrix to uh, that is getting applied on U. Yeah. Okay. Uh, yeah. So basically, you have to do R times U and find out the vector V. Um, yeah, this is a general question on QR decomposition. So if you write A equals QR, uh, the columns of A form an orthogonal basis of Rn, uh, and R is a symmetric matrix. No, R is not a symmetric matrix because R is an upper triangular matrix. So, uh, um, in almost all cases, it's not going to be a symmetric matrix. Um, unless A itself has orthogonal columns, and in which case, uh, uh, yeah. So I mean, when can R be symmetric? So R is symmetric. R is symmetric in this case implies that R is diagonal. So all entries above its diagonal must be equal to 0, and then that implies that uh, A uh, must have orthogonal column vectors. But that is of course not given to you, so we do not know if A has orthogonal column vectors. The columns of Q form an orthonormal basis of Rn, and R is used to solve the upper triangle system Rx equals Q transpose B using back substitution. Yeah, we use back substitution. The columns of R form an orthonormal set, and Q is the lower triangular matrix. Uh, yeah. I guess the rest of the options can be easily verified. Yeah, this is a easy problem. Uh, look at the last problem. Again, in this case, A has linearly independent columns. Um, so if A has linearly independent columns, so the first thing that we can say is that um, A is a uh, A is a tall matrix. So A looks like this. So basically, what it means is that M must be greater than or equal to. Um, so A can look something like this. If the gram matrix of A defined as A transpose A, uh, yeah. So the gram matrix of any matrix is just defined as A transpose A. If you write A as QR, then A transpose A. I mean, this is just routine checking. Is R transpose Q times R. That is equal to R transpose R. Yeah. Um, okay. I think we know the answer to this question now. Yeah. So that solves the assignment problems from week 4. Um, yeah, we still have some time left. So if you have any questions, you can ask me. Otherwise, uh, we can look at some other problems. I can choose and pick and choose some problems. Oh, okay. Someone said Q7. What is Q7? Oh, okay. I think I missed Q7. Sorry. Look at Q7. So in the LU decomposition of A, if the diagonal elements of U are both 1. Oh, yeah. I mean, this is how you solve a question like this. Uh, well, you have to basically just solve uh, something like equation like this. So N11, N21, just plug it in and solve this. Okay. So what do you get? You get um, so you get L11 equals to L21 equals 4. Um, then for the second row, you get uh, uh, well, I mean, for the second row, you get basically this. You get U times L11, L21 plus 0 comma L22 is equal to 2 comma 9. Yeah, I just solve it. Easy question. Yeah, this is how you solve a question like this. Plug in the values and you solve it. Yeah, I hope it's clear. Okay. So since we have some time left, let's look at some other problems before we wrap it up for today. Uh, let's see. Just give me a minute or two. Okay, let's look at this problem. Right, so this is a slightly theoretical problem. We have to prove this inequality. Now, determinant of A is less than or equal to uh, the product of the norms of the vectors. Um, okay, let's solve this uh, and let's see how we can use the QR decomposition to solve this. Okay, so we're given a matrix A in Rm cross M. Write A as A1 to Am. These are column vectors. We can write A as equal to so there are two possibilities. Either A is uh, either A is a non either A is degenerate, meaning that the rank of A is less than M, in which case this inequality holds trivially. But the other case is A is full rank. So we can write this A as equal to some Q times R. Q is an orthogonal matrix, right? So the determinant of Q uh, is equal to 1. The absolute value of the determinant of Q is always going to be equal to 1, right? So the determinant of A is equal to the determinant of R. I'm talking in absolute values. So what is R? R is an upper triangular matrix. So if you have an upper triangular matrix, then so this is the basic stuff. So if R is upper triangular, then determinant of R norm is equal to the product of its diagonal entries. Right. This is easily checked. So now, what are the diagonal entries of R? Okay. So recall that we constructed this QR decomposition using the Gram-Schmidt orthogonalization process. So uh, in particular, uh, for any k in general, you will write this pk as equal to uh, rkk times qk plus plus uh, rk minus 1 uh, k q k minus 1 and so on, right? uh, so basically what you're doing in this process is as follows. So you have computed a series of vectors q1 up to qk minus 1 which are uh, which are orthogonal, and let's define the subspace uh, q k minus 1 as equal to the span of these vectors. What we're doing over here in the Gram-Schmidt process is that we're writing this pk as equal to uh, some vector over here, which I'm going to call it as pk prime, plus a vector uh, pk tilde that belongs to this qk minus 1. So pk tilde belongs to qk minus 1, and pk prime is orthogonal to this thing, right? So if you write two vectors, so if you can write a vector p as equal to some p1 plus p2, where p1 and p2 are orthogonal to each other, right? Then norm of p is equal to uh, p1 squared plus p2 squared, right? Okay. So the diagonal element rkk over here, the norm of this element is equal to the norm of this element. Now, of course, pk squared, pk norm squared is equal to pk prime norm squared plus pk tilde norm squared. So of course, from what we get from here, that rkk mod is less than, so rkk mod is basically equal to uh, pk prime mod, and that is less than or equal to pk squared, pk mod basically. Now the determinant of a is, so what is the determinant of a? Determinant of a is equal to determinant of r, and that is equal to the product of these rkk's. But each rkk has a small is smaller than this, so this is smaller than or equal to uh, yeah. So this is smaller than or equal to uh, product of the norms of these vectors, and that is uh, and that concludes the proof of this problem. Okay. Um, I guess we're out of time today, so I won't be able to discuss any problems further. Um, if you have any questions, you can ask me next week. I'll try to answer them. As always, thank you for your attention.